Let's kickstart the topic by revisiting the term binomial. In mathematics, a binomial is an algebraic expression that contains two terms, right? So we know that bi is 2, and so as a whole binomial is two terms. For example, a plus b, that's a binomial term. 3x minus 4y, binomial term. Root of 5 plus x, a binomial term. Now, what is that we are doing over here? Well, when we have a binomial term raised to some power, say square. So what is it? A square plus 2ab plus b square. But what if I had, say, to the power of 4? Well, we can solve this by a plus b the whole square into a plus b the whole square. It's lengthy, but it's doable. What if we had this to be 40? So the same thing has to be done 20 times. That's not practical. But we are able to expand this, and there is a pattern that occurs over here. Whenever we expand a binomial term, there's a pattern that occurs. So let me show it to you guys. So we have a plus b the whole to the power of 1, a plus b whole to the power of 2, a plus b whole to the power of 3. So this we know, right? A plus b whole to the power of 1 is a plus b itself. A plus b whole square is a square plus 2ab plus b square. And a plus b whole cube is a cube plus 3ab square plus 3b square a plus b cube. Now let me raise it to the power of, say, till 8. So there is a pattern, that's what I mentioned. So the pattern is with everything over here. Let's start off with a, the power of a basically. So let me take up a to the power of 4. Or let me take up a to the power of 3 itself. I mean a plus b the whole cube basically. A cube plus b square plus b to the power of 1 and b to the power of 0. Sorry, a to the power of 1 and a to the power of 0. Let me take up a to the power of a plus b whole to the power of 4. We start off with a to the power of 4, a cube, a square, a to the power of 1 and a to the power of 0. Let me take up a to the power of 6, a plus b whole to the power of 6, that is. So a to the power of 6, a to the power of 5, 4, 3, 2, 1, and here it is a to the power of 0. The last expression, 8, 7, 6, 5, 4, 3, 2, 1, 0. So the powers have a very particular pattern. What about b? Well, b over here is b to the power of 0, 1, 2 and b to the power of 3. So let me take up this. So a plus b whole to the power of 6. The b powers look like b to the power of 0, b to the power of 1, 2, 3, 4, 5 and 6. I hope you guys are able to zoom in and see the expansion. And we have b to the power of 0, b to the power of 1, 2, 3, 4, 5, 6, 7, 8. So there's a clear pattern when it comes to power. Now the only thing that we need to do is powers are done, right? So when we expand it, what else will we get? A square plus 2ab plus b square. We will also get the coefficients, the numerical coefficients. So let's look at the numerical coefficient. Let me start off with here. So this is 1 and 1. Here the numerical coefficient is 1, 2, 1, 1, 3, 3, 1. Okay, there looks like a pattern. 1, 4, 6, 4, 1. Not so much. 1, 5, 10, 10, 5, 1. Now it's not making utna sense. 1, 6, 15, 20, 15. No. Well, we are not able to look at the numerical pattern over here. Well, I'll show it to you guys in a different way. Imagine that all this empty space has zeros, right? Equally spaced zeros, and there's a 1. Now, the next pattern is that. So how did I get this? 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 0 is 1. Are you getting the flow? 0 plus 1 is 1, 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 0 is 0. Right? So there is a pattern, is it not? Clear pattern. 1 and 0 is 1, 1 and 3 is 4, 3 and 3 is 6, 3 and 1 is 4, 1 and 0 is 1. 6 plus 4 is 10, 4 plus 1 is 1, 4 plus 1 is 5, 1 plus 0 is 1. So there is a clear pattern, right? 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20. So there is a clear pattern, is it not? So this can be better represented with combination. This is, say this is 0, 1, 2, 3, 4, 5, 6. So this is a plus b whole to the power of 6. This is 6c0. With the help of combination, I will be able to express all of this. This is 6c1, 6c2, 6c3, 6c4, 6c5 and 6c6. So this too can be represented with a particular pattern. Okay. So looking at all of this, what is that we are able to tell? The pattern emerges. The pattern emerges with powers of variable as what? As increasing and decreasing whole numbers. Agree? Then powers, that was powers. Then we have variables. Then we have coefficients. So this too can be represented with increasing NCI. So basically this I will raise from 0 till n. Combination basically, is it not? Right? So that's what the pattern which we saw. So since we have a pattern, what does maths do? It generates a formula, and that formula or idea is your binomial theorem. Okay. So let me show it to you guys. So let me take up the general expression a plus b whole to the power of n. This can be expanded in this manner. NC0. I'm going to start off with writing the numerical coefficient NC1, NC2, NCn minus 1 and NCn. Right? Then we will multiply this with a to the power of n, e to the power of n minus 1, e to the power of n minus 2, a to the power of 0 and a to the power of 1. So this is the pattern that it will follow. While the second term will follow b to the power of 0, b to the power of 1, b to the power of 2, b to the power of n minus 1 and b to the power of n. That's the pattern. So since there is incremental form of numbers, we can use something called a summation notation. So this is something that you guys will learn in time. Don't worry if you don't understand this. It's not that complicated also actually, to be honest. But yeah, you will understand in time. So I can represent this entire thing in a better manner actually. This is known as summation. We have studied summation actually, right? Oh yeah, we have studied. We have studied in statistics. But not the entire thing, not the entire representation. So I running from 0 to n. So NCI, a to the power of n minus I, b to the power of, this is I. That's your representation. Okay, this is a summation notation. So what it tells is I should run from 0 to whatever the number is, whatever the power is basically. So it's related to the power. So it's related to the power. And this I is, well, it runs from, this is a set of bunch of integers, or in this case whole numbers. So 0, 1, 2, 3, 4 till whatever the last power is. Okay, so that's what binomial theorem does. A binomial theorem provides a formula like this for expanding a binomial to any power. Okay, so this is the reason, not reason, this is what it does. It's a formula. It's giving a formula to expand binomial terms to any power, where n is, we are looking at whole numbers only, by using a combination of coefficient and exponents, right? So let us make use of this, and let's look at a plus b whole to the power of 2. So as per this notation, it's basically summation of I is equal to 0 to, here it has to be 2c I into a to the power of 2 minus I into b to the power of I. So this summation notation tells us to expand in this manner. So we have 2c 0. So first thing is we have to make wherever I is, make it as 0, and then make it as 1. Sorry, this is a to the power of, and then make it as 2. And on simplifying this, we'll say what is that we'll get. See this, if you guys are familiar with permutation combination, which you guys have to be, please don't do this chapter without that. So this is 1, this is 2, and this is 1. So this is 1 into a square into 1, so a square plus 2 into a to the power of 1 into b to the power of 1, 2ab, plus 1 into b square, that is b square itself. And that's nothing but your a square plus 2ab plus b square, expansion of a plus b whole square, right? So yes, we are able to expand binomial expressions to any power. We'll be able to expand that just by remembering this particular formula. Okay, so that's your introduction. See to that you guys write everything. There's nothing much, but on this there are complicated questions. If you don't understand this, you won't be able to do that.